I'm going to do an example problem where you need to find the electric field at a point P due to other charges that are arranged in a way such that you're going to have to resolve forces into X and Y components, or electric fields into X and Y components. So this is problem 30 in chapter 15 of the Serway College physics book. Okay, so if we want to find the electric field at point P due to those other three charges, the first thing we have to do is we have to find the electric field due to each of those other charges individually. So let's number them so that we can keep track of which is which. So let's call these 1, 2, and 3. Oop, that's not a very good 3. 1, 2, and 3. And let's find first the magnitude of the electric field due to charge 1 at point P. So that's going to be, well, we'll use the equation KQ over R squared. So K is 9 times 10 to the 9 Newton meters squared per Coulomb squared. And Q is 3 nanocoulombs, so 3 times 10 to the minus 9 if we convert to SI units of charge. And R is 4 centimeters. Again, we need to convert to SI units, so that's 0.04 meters, and we square that. Plug that into your calculator, and you get 1.688 times 10 to the 4 newtons per coulomb. All right. Now, how about the magnet? Now, that's just the magnitude of the electric field due to charge 1. That doesn't tell us anything about the direction. We'll have to get the direction later, and we'll do that in the next step. First, let's just find the magnitudes. Okay, so the magnitude of charge number 2, electric field, is, again, 9 times 10 to the 9, and I'm not going to write the units out every time. They're the same, times 2 times 10 to the minus 9 over, and that distance is also 0.04 squared. Notice that I didn't plug in the negative because we're only looking for the magnitude here, not the direction. We don't really get the direction from this equation. We get only the magnitude. You have to get the direction by thinking about the definition of electric field. So this would be, when we plug that in, it's 1.125 times 10 to the 4. 1.125 times 10 to the 4 newtons per coulomb. Okay, and then if we do it for charge 3, we see that the magnitude of charge 3 is the same as it is for charge 1, and the distance is the same as it is for charge 1. So that must mean that the magnitude of charge 3 is equal to the magnitude of charge 1. And these 30s have gotten moved. We'll see, they're supposed to be marking the angles. Okay, they're all at 30-degree angles, and all of these distances are 4 centimeters. Okay. So now it's time to worry about the direction. To get the direction, we use the definition of electric field, which is that if you were to put a positive test charge at point P and it experiences an electric force, then the electric field points in the direction of the force that's experienced by that positive charge. So, what would the direction of the electric field due to charge 1 be? Well, if I put a positive charge at point P, charge 1 is also positive, so it would repel the positive charge that was at point P. The electric field due to charge 1 at point P is pointing that way, right along that line that connects the two charges. Okay. And for charge 3, that's going to be like this. All right, charge 2, that's a negative charge. So if I put a positive charge at point P, the negative charge, charge 2, would pull it in the negative direction. It would pull it over to the left. So that electric field is pointing that way. So now we have the magnitude and direction of each of the individual electric fields, but to find the total electric field, we need to resolve the individual electric fields into components and add them as vectors. So what we need, then let's find the x component of the electric field due to 1. Well, and actually I don't want to find just the magnitude, I want to find the direction too. So that's going to be, well, let's draw a triangle so that we can use our trigonometry skills. So we're going to have the y component that way and the x component that way. And it looks like then if that's a 30-degree angle, then the x component is adjacent to the 30-degree angle, so that I'm going to have to use cosine. E1x is equal to the magnitude of E1 times the cosine of 30, and that is 1.461 times 10 to the 4th newtons per coulomb. E1y, since y is adjacent to the 30-degree, or is opposite the 30-degree angle, that's E1 times the sine of 30, which is 8.438 times 10 to the 3 newtons per coulomb. Okay, and now let's pay attention to, is this positive x and y or negative x or y? So the x one looks like it's pointing to the right, so that's plus x. But the y one is pointing down, that's minus y. Okay, now we do the same thing for charge 2. Well, charge 2 is going directly to the left, so that doesn't have a y component, that's easy. E2y equals 0. And the x component is just the magnitude of the whole thing. It is all an x component. E2x is the same as the magnitude of E2, and that is, we found it to be 1.125 times 10 to the 4th newtons per coulomb, and that was in the negative x direction. All right, now we do charge 3. Well, if you look at the drawing, it looks like the distances, the angle, and the magnitude of charge 3 is all the same as charge 1. So I think the x and y pieces are going to have the same magnitude. The only thing that's different is the direction might be a little different. So let's draw in the vector for 3. So it's going to have a y component like that and an x component like that. So its x component is the same, exact same as for 1. So let's write that down. E3x is going to be the same as E1x. I mean, if you didn't recognize that, you could use trig to find it anyway. I mean, it wouldn't, there's nothing wrong with using trig to find it again. I'm just taking a little shortcut since we noticed. So that's 1.461 times 10 to the 4th newtons per coulomb. And also in the plus x, well, the y component is going to be the same magnitude as the y component of charge 1, but it's going to be negative instead of positive. So I'll go over here, E3y equals the same as E1y, 8.438 times 10 to the 3. but it is in the positive y, not the negative y. Okay, so now that we have resolved all of the electric fields into their x and y components, we find the total electric field by adding up all of the x's and all the y's. So the total x component, ETX, is E1x plus E2x plus E3x. Well, E1x and E3x add are the same. They're 1.688 times, or no, they're 1.461 times 10 to the 4. So 1.461 times 10 to the 4 plus E2x is 1.125 times 10 to the 4. And then E3x is the same as is E1x, so that's 1.461 times 10 to the 4. You add all of that up, and you get that ETX is, well, let's see, have I made a mistake somewhere? 1.461 times 10 to the 4. Oh, yes, I'm about to make a mistake. I caught it just in time. The x component of number 2 is negative. I need to subtract that. I almost forgot to take into account the fact that the x component of number 2 is negative. So let's erase that negative, and I'll put it there in red so we don't forget it again. This is plus. Okay, and then if you add all of those up, you get that the total x component is 2.923 times 10 to the 4 newtons per coulomb. Okay, and the y component, well, the x component of number 1 and the x component of number 3 cancel each other out. So E total y is just, and there is no y component for number 2. So since 1 and 3 cancel each other's y and 2 doesn't have a y, then ETY is 0. All right. But let's say we had a situation in which ETY was not 0. How would you find the magnitude of the total electric field? Well, what you would do is say that the magnitude of the total electric field, you'd use the Pythagorean theorem. So you would just have ETX squared plus ETY squared. And in our case, that's equal just to ETX, which is 2.923 times 10 to the 4 newtons per coulomb. But if you had a y component, a total y component that was not 0, you would use this equation to find the magnitude of the total electric field. And you could use trigonometry to find the direction of the total magnetic field depending on what ETX and ETY were. Okay, now that's part A of the problem. Part B of the problem is if we were to put a 5 nanocoulomb charge at point P, what would the force on it be? Well, you might think, your first thought might be, oh my gosh, am I going to have to go through all this math to use Coulomb's law because I've got a 5 nanocoulomb charge at point P. I'm going to have to find the force due to charge 1 and the force due to charge 2 and the force due to charge 3 and add those all up as vectors. Oh my goodness, I've got another bunch of math to do. Well, you could do that, and if you didn't make any mistakes doing it that way, you would get the right answer, but there's a much faster way. And that is that the force on a point charge due to an electric field is F equals EQ. We already know E, and we're given that we're going to put a 5 nanocoulomb charge there. So if I put, so F on a 5 nanocoulomb charge at P would just be the electric field 2.923 times 10 to the 4 times 5 times 10 to the minus 9, and that is 1.461 times 10 to the minus 4 newtons. So no reason to go through all of that math again. We already did it. All right, that is the problem.